Hello and welcome to Power System Analysis 2. We're in module 3.3. From the previous example, we will be seeing a couple or more examples, but these examples are connected to the previous examples. So just before starting this problem, let us go to the previous example. So in the previous example, we had two such generators which have been running together and supporting a particular load. So we have seen that this is table 7.1 in the book. This table is important, so you can have for different values of lambda what is the distribution of power of one generator to the other and the total power, and under that you have this graph. Actually in the previous example, this graph is supposed to be like you can get the values, like I have said that you can get, say, for 150 megawatt the lambda is 52.22. see, you can get it from here only. Okay, so if I zoom in the graph, you can see this is a plot of incremental cost for the total power generation. Okay, so it is for the total system. Now you can see at 150 you'll have certain around between 50 and 55. So from this graph only you can get the value of the lambda. Now how is this graph obtained? Graph is just the plotting of these values, the lambda values or the incremental cost values with the power. So you can see we have plotted 35, 44, 50, 55. So you can see 35, 44, 50, 55, all these all these values are plotted, and then when we want to find a particular value at a particular power, we can actually get the value of lambda at this point from this graph only. So you can refer to this graph or you can refer to this table. Okay, so let us continue with the example 2. Now example 2, as I have told you, is a continuation of example 1. So it says that for the plant described in example 7.1, that is the example we have seen previously, find the saving in fuel cost in rupees per hour for the optimal scheduling of total load of 130 megawatt as compared to the distribution of the same load between two units. That means what? Now they have said to compare. We have a load of 130. Now we compare with the optimal distribution to the to this concept that both generator will generate equally. Okay, so if both generator generates equally, it is 65 megawatt per generator. Okay, so it is said that if the generator generate 65 megawatt per generator and two generators generates the same, I am getting 130 megawatt. Will that be economical, or the actual we obtain from this lambda value, will that be economical? So let us see. So I have said that if they run together with the same power, it will be 65 megawatt to produce a 130 megawatt load. Now the solution, it says that example 7.1 reveals that the unit 1 should take up a load of 50 megawatt and unit 2 should take a load of 80 megawatt. How are you getting this value? We go to the table. So 130, you see total plant is 130, unit 1 should take 50, unit 2 should take 80 megawatt. So unit 1 should take 50 and unit 2 should take 80 megawatt in order to have an optimal scheduling of the generators economically. Okay, Now if we say that no, I think if the two generators are working together at the same power, that would be more economical. Let us see. So if the generators will generate the same amount of power, it should be 65 megawatt. Now generator 1 was scheduled at 50, now it is 65. So we are going to integrate the total cost between 50 to 65. So the cost of generator 1 actually increased, right? And it increased by 772.5 rupees per hour, which is obtained by integrating the cost function between 2 points 50 and 65. Why 50? Generator 1 was at 50, but now you are saying that 65 would be better. So that was the increase from 50 to 65. So the cost would be 50 to 65. Okay. Similarly for unit 2, it was 80, now you are saying 65. So you have to reduce. So the reduction in the cost would be 721. Okay. Now you can see if we use the generators as equally 65 megawatt, there will be a total of 50.625 rupees per hour extra. So you can see if the two generators working together with the same amount of power, it is not economical, because you'll have to pay, or you have to spend 56 rupees per hour more. Okay, so you can see the total yearly saving would be around 4,43,475 rupees. Okay, do not go by these numbers. These numbers are not at all exact, but these numbers give you a general idea how the thing is done. Okay, now you have one more example. This is one more example that is very interesting. You have again two generators with two cost functions. Got it? Now these two generators are supplying a load, and the load, you can see, it is for an entire day between Sunday to Monday. Between Sunday, that is starting at night 12 o'clock. Okay, you have the entire Sunday, and from, you can see, during the night or evening time, the load is at 76 megawatt. Now during the noon, it is 220 megawatt. Okay, till Monday, this is the daily load curve. Now we have to see an economic way to distribute the generators. We have two generators to supply this load. The load curve is given. Now it is an example taken from the book. So the book says that let us assume a daily load cycle given in figure 7.5. This is this figure. Also assume that the cost of rupees 400 is incurred in taking either unit off the line and returning to its service after next 12 hours. So if we think that it would be economical to switch one of the generators off, okay, when the load is low, then you have to pay 400 rupees extra in order to switch it off and again switch it on again, okay, after 12 hours. Now consider 12-hour period from 6 a.m. Morning to 6 p.m. in the next morning. So we want to find out whether it would be more economical to keep both units in service for this 24-hour period, or to remove one of the units from the service for 12 hours and then 12 hours of the light load. So we are comparing whether it is economical to run the two generators together, or switch off one and then run it. Okay, so for the 12-hour period, the peak period, the load is 220. Okay, now 220, what is the economic way of distributing the load among two generators? Well, let us go to the graph. Wait 1 second, I'll just say 220 megawatt. So a 220 megawatt, unit 1 should be 100 megawatt and unit 2 should be 120. 100 and 120. So PG1 is 100, PG2 is 120. Now total fuel cost is that you put the value of PG1 and PG2 in these two equations and you add them up. Okay, so the total fuel cost is now coming to be rupees 1,27,440. Okay, for this particular period. Now if both units operate in the light load period, that is the 76 megawatt from 6 pm to 6 am, then from the same table we can get the optimal schedule as 20 and 56. So for 76 megawatt, let us check. See, you can see the second row, 76 megawatt, you have 20 and 56. So use that value, you get the total fuel cost at 37,000. So for an entire day, what is the fuel cost? 37,584 plus 1,27,440. That gives you 1,65,000 and 24 rupees for the entire 24-hour period. Okay. Now you are saying that no, I think it is much more economical if we switch one generator off. So if only one unit is run during the light load period, it is easily verified that it is economical to run unit 2 and put off unit 1. Okay, how do you know it is economical? Let us do it. So the total fuel cost bore by unit of any one of the unit, let's say unit 2 itself. Okay, because unit 1 is costlier, so unit 2 you can use 76 and you are putting off unit 1. So see, we add you put that 76 in the C2 equation. Okay, and we get the total fuel cost is 1,64,664. Okay, the total operating cost for this case would be the total fuel cost plus the startup cost of unit 1. Remember that. So that was again added. It gave 1,64,604. The comparing to earlier case, it is clear that it is economical to run both the units. You can see for the if you want it, unit is switched off, you'll have a price of 1,65,000, where here it is 64. Now it is 1,65,024. So you have slight benefit here if we run the generator. Okay, so this is how a general unit commitment problem comes. Okay, so this is the end of this lecture. Thank you.